Not okay. Are Bappa and Shushmita not present today? Oh, there's
Sir, I
Bappa.
am present.
Okay. So Roshan and Shushmita need to join. Okay. Could you just ask them to join? They were here a second ago, no? Roshan was here, I think. Okay. So I think Shushmita is not joining today then. So okay. So are there any questions from the previous class about the geodesic equation, geodesics and the geodesic vector field?
Sir,
Yes.
sir, the last day you were talking about Koszul formula,
Yes. Yes.
and I am asking a slightly deviated question. So I have seen something called Koszul complex. So are they two somehow related?
No, no, no. It's the same person, Koszul, but the two are not related. No. I don't really know what the Koszul complex is. I think it's a chain complex. So, as far as I remember.
I actually searched in the Wikipedia, and they have referred to some Lie groups, etc. part, but I could not get anything out of it.
Right, right. No, it's not. I mean, it's not related to the Koszul formula. It's just. Any other questions? Okay, so let's start then. So, let me share. So, okay. So last time we talked about the geodesic equation. We first proved the existence and uniqueness of a affine connection, which is on a Riemannian manifold, which is compatible with the metric and which is symmetric. So there is a unique such connection, which is called the Levi-Civita connection or the Riemannian connection. And then using that, we were able to define geodesics. So a connection gives us a notion of covariant differentiation along curves. And if I have a smooth curve gamma, then gamma dot, the tangent vector, that defines a vector field along the curve gamma. And we say that gamma is a geodesic if the covariant derivative of gamma dot is 0. Okay. So capital D dt of gamma dot is 0. So we notice that this implies that the speed of any geodesic is constant. That means the norm of gamma dot is a constant. And we wrote out, we saw that the equation ddt of gamma dot equal to 0, once you write it in coordinates, it's equivalent to a system of n second order differential equations, which are nonlinear differential equations. Okay, this equation here. where the nonlinear term involves the Christoffel symbols and the first derivatives. And then we saw that if you look at the curve lifted to the tangent bundle, so what that means is, given a curve gamma, you get a curve in the tangent bundle, gamma t comma gamma dot t, right? This is a curve of tangent vectors. So this is a curve in the tangent bundle. And we saw that gamma was a geodesic if and only if this curve in the tangent bundle, so there we have coordinates, 2n coordinates, x1 to xn and y1 to yn. These y1 to yn are nothing but dxi's, right? These are dx1 to dxn. So these are the natural coordinates on the tangent bundle. So in terms of these coordinates on the tangent bundle, a curve gamma in M was a geodesic if and only the lifted curve gamma t comma gamma dot t in the tangent bundle satisfies a system of first order equations. Okay. So this system of first order equations. So notice that if you look at the geodesic in M, then it satisfies a system of second order equations. But if you look at the lift in the tangent bundle, then those second order equations get transformed into a system of 2n first order equations. Okay. So this is similar to what you might have learned in school, right? How to transform a second order equation, let's say just one second order equation, into two first order equations, right? By introducing a new variable, y is equal to x prime. So that becomes your first equation. And then the equation involving x double prime becomes an equation in terms of y prime. So it becomes a first order. So you get two first order equations. So that's essentially what we're doing here. We're converting this second order equation in M into a first order equation in the tangent bundle. And once you have a first order equation, that can be described by a vector field, right? First order ODEs are the same thing as vector fields on the manifold. So we get a vector field on the tangent bundle, G, which a priori depends on the coordinates X. So in terms of the coordinates, remember that our coordinates are x1 to xn, y1 to yn. So the basis for the tangent space of the tangent bundle will be spanned by del del x case and del del y case. So in terms of this basis, this vector field G is given by this formula. And then what we showed is finally is that this vector field, which a priori it might depend on the choice of coordinates x1 to xn, actually it does not. Okay, so if x and z are two coordinates on U, then gxu is the same as gzu. And so therefore we get a global vector field G on the whole tangent bundle, such that gamma, a curve in M, a smooth curve in M, is a geodesic if and only if the lifted curve T maps to gamma T gamma dot T is an integral curve of this vector field G. Okay. And all integral curves of G are of the form gamma T gamma dot T, where gamma is a geodesic. Okay. And so we did the proof of this. Let me recall it for you. So you take a point Q in U, and you take a tangent vector V and TQM, and then you let alpha be an integral curve of G, such that so this is a curve in the tangent bundle whose initial value alpha 0 is Q comma V. So then because alpha satisfies the vector field G, that means that if I write it in terms of the coordinates x1 to xn, y1 to yn, then because it's an integral curve of G, that means that the coefficient of del del xk in this curve, in alpha prime. So that will be dxk dt. So dxk dt is equal to yk, right, for all k. And so that means that the tangent vector v is equal to gamma prime, right? Okay. Right, because v in coordinates was the vector y1 to yk, y1 to yn, and the yi's are given by dxi dt, which are the coordinates of gamma prime, right? So that means that v is equal to gamma prime. Okay, so this curve is of the form gamma comma gamma prime, and because it satisfies the geodesic, this vector field g, this is a geodesic, right? So alpha is of the form gamma gamma prime, where gamma is a geodesic, and therefore alpha is also an integral curve of the vector field g sub zu, right? Because we saw that any geodesic is an integral curve of gzu, where z is any coordinate. And so alpha is an integral curve of both gxu and both gzu. So if I look at alpha prime 0, then that will be G, on the one hand, gxu of qv, and it will also be on the other hand, gzu of qv. And so therefore gxu is identically equal to gzu. Is this okay? Any questions? Yes?
Sir,
Yes.
how do you prove that all the integral curves of G are of this form?
That's exactly what we proved in the proof of this proposition, right? We took alpha to be an integral curve of G, and we showed that it's of the form gamma gamma prime, where gamma is a geodesic, right? So
Yeah, how do you say that?
yeah, so we did that at the end of last class. Let me just show you. So suppose alpha is an integral curve of gxu. So if I look at the coordinates xy on the tangent bundle, so alpha has some gamma t vt, right? Where vt is a tangent vector in the tangent space at gamma t, right? Yes, alpha t I can write in this form.
Yes.
Now look at xy composed with alpha. So this is a curve in R2n, right? So this is of the form x1t xnt and y1t up to ynt. And what are y1 to yn? By definition, these are the coefficients of vt with respect to the basis del del x1 to del del xk of the tangent space, right?
Yes.
Yes? So vt is summation over k, ykt del del xk. Now what does it mean for alpha to be an integral curve of g? It means that alpha prime is equal to g of alpha, right? Yes?
Yes.
Now look at the formula for g. G is summation yk del del xk plus summation over k minus sum over ij gamma ijk yi yj del del yk, right? And what is alpha prime? Alpha prime will be summation over k dxk dt del del xk plus dyk dt del del yk, right? So alpha being an integral curve of g means that dxk dt has to equal yk of t, right?
Yes, sir. No.
Okay. And also dyk dt has to equal minus sum over ij yi yj gamma ijk, right? Yes?
Yes, sir.
Okay. So now what is Vt then? Vt was summation ykt del del xk, but ykt is dxk dt. So this becomes sum over k dxk dt del del xk, which is gamma prime t, right? Yes?
Yes, sir.
And also, what is this equation dyk dt equal to minus sum over ij yi yj gamma ij k? This means that dyk dt will be d squared. So dyk dt, since yk is dxk dt, this will be d squared xk dt squared, right?
Yes, sir.
Yes. And this is equal to minus sum over ij yi yj gamma ij k. And this is equal to minus sum over ij dx I dt, because yi is dxi dt, and similarly dxj dt gamma ijk, right? Yes.
Yes, sir.
In other words, x satisfies the geodesic equation, the second order equation, right? The second order system of equations. Is this clear?
Yes, sir.
So therefore, the curve x1 to xn, that is the curve gamma t. Gamma is a geodesic. Is this clear now?
Yes, sir.
Yes?
Yes, sir.
Okay. So therefore, any integral curve of this vector field G is of the form gamma comma gamma prime, where gamma is a geodesic. All right. And vice versa. If gamma is a geodesic, then gamma comma gamma prime is an integral curve of G. Is it clear?
Yes, sir. Clear.
Yes? Okay. Okay. Gamma is a geodesic, and alpha t is equal to gamma t gamma prime t. So does anyone have any questions about this proposition, this lemma? Is it clear now? Okay. All right. So this vector field, you can see that its coefficients are smooth functions of the coordinates, right? Because the Christoffel symbols are smooth, and the yi's are just coordinates, are smooth coordinates on the tangent bundle. So this is a smooth vector field on the tangent bundle. This is called the geodesic vector field, okay? Because its integral curves are lifts of geodesics, right? They're of the form gamma comma gamma prime, where gamma is a geodesic in M. All right. So now we get immediately as a corollary that by the local existence and uniqueness theorem for vector fields on a manifold, right, which follows from the local existence uniqueness theorem for ODEs in Rn, that given a point P in M, there exists an open neighborhood V of P. There exists delta positive and epsilon positive, and there exists a C infinity map, a smooth map, gamma, from the interval minus delta comma delta cross a subset of the tangent bundle script U into M, where what is script U? It is the set of tangent vectors Q comma V, where Q is a point in V, V belongs to TQM, and the norm of V is less than epsilon. Okay, the norm of V is less than epsilon. So in other words, I look at all the points Q in the neighborhood V of P. In each of those points, I look at the ball of radius epsilon in the tangent space with respect to the Riemannian norm, and then I take the union of those balls. So this is an open neighborhood of the zero vector in the tangent space at P, right? This is an open neighborhood of the zero vector in the tangent space at P. And so this is a subspace of subspace of the tangent bundle of V. And this map gamma from minus delta comma delta to U is of the form, it satisfies for any QV in U, the curve T maps to gamma of T comma Q comma V, where QV are fixed. This is, and T belongs to minus delta delta. This is the unique geodesic such that gamma 0 is Q and gamma dot 0 is V. All right, so this is the unique geodesic with initial conditions Q comma V. Is it clear? So how do you prove this? The proof is just the existence uniqueness, local existence uniqueness theorem. You take the point P comma 0 in the tangent bundle, right? So that has a neighborhood in the tangent bundle in which, and there is a delta positive, so that for every point in that neighborhood, there is an integral curve of the geodesic vector field G, starting from that point in the tangent bundle, which is defined for time delta from on the interval minus delta to delta. Right, so any neighborhood of the point P comma 0 contains a neighborhood of this form. Set of points Q in V and V in TQM such that norm V less than epsilon. Is this clear?
Yes, sir.
Yes, this is okay. Any questions? Okay, so this neighborhood script U, think of this as a neighborhood of the point P comma 0 in the tangent bundle, right? So the local existence uniqueness theorem tells you that in a neighborhood of P comma 0, we will have unique integral curves of the geodesic vector field defined for time T, right? So that will give us this map. Is it clear? So this gamma will be basically, you get the integral curves in the tangent bundle, then you project them down from Tm to M, right? You have the natural projection from Tm to M, which sends a tangent vector, I mean, Q comma V maps to Q. So you just project it down. The projection will be a geodesic below, right? Is it clear? Okay.
Sir, can you repeat this part?
Yeah, so I mean, what did we prove? We proved that if I take an integral curve of G, then it's of the form gamma comma gamma prime, right? Where gamma is a geodesic, right?
Yes, sir.
So an integral curve of G lives where? It lives in the tangent bundle, right? Yes?
Yes, sir.
Now we have a natural projection from the tangent bundle Tm to the manifold M, right?
Yes, sir.
Q comma V maps to Q, right? We have the
Yes, sir.
natural projection. So all I'm saying is, what does this previous proposition tell us? It told us that if we take any integral curve of G, then the projection of it below will be a geodesic in M, right?
Yes, sir.
Right, the integral curve will be a curve in Tm. You project it down, you get a curve in M. That curve in M is a geodesic.
So, to summarize, can we say that integral curves of G are essentially determining all the geodesics on M by the
Yes,
first projection?
Yes, yes, yes. And vice versa, geodesics in M determine integral curves of G, right? That's what we proved in this lemma. If I have an integral curve of, if I have a geodesic below, then I have a natural lift to the tangent bundle. T maps to gamma T, gamma prime T, right? Yes?
Yes, sir.
So that lift will be an integral curve of G. So there is a one-to-one correspondence between integral curves of G and geodesics in M. Right? Given a geodesic, you take its lift, gamma comma gamma prime, that will be an integral curve of G, and vice versa. Given an integral curve of G, you take its projection below, that will be a geodesic in M. Is this clear? That's what we proved all along, right?
Yes, sir.
Okay, so is the proof of the proposition clear now? This proposition here, that we get this smooth map gamma from minus delta delta cross U to M. Yes? Any question about this? Any question?
No, sir.
Should I write out the proof? You want me to write the proof? I can write out the proof. I mean, it's just 2 lines. So, so let me just write it out. So you have P belongs to M. So you have the vector P comma 0, right? So this belongs to Tm. Okay. Now and you have G, which is a smooth vector field on Tm, right? Yes? Okay. So by local existence uniqueness for ODEs, there exists a neighborhood, let's call it script V, of P0 in the tangent bundle. Okay, so script V is a subset of the tangent bundle, and there exists delta positive such that for all Q V belongs to script V, there exists a unique integral curve alpha from minus delta comma delta to Tm of G such that alpha 0 is Q comma V, right? Yes, this is okay,
Okay, sir.
right? Yes, okay.
Yes, sir.
Now, now V is a script V is a neighborhood of P0. So V neighborhood of P0 in M, in Tm implies V contains a neighborhood of the form U, which is QV in Tm, such that Q belongs to V, V belongs to TQM, and norm V is less than epsilon. So let me call this curve alpha QV. Okay. So, so this U will exist for some small enough neighborhood V of P in M and some epsilon positive. Is this clear? Yes?
Yes.
Because look, if I take coordinates on my manifold Tm, x1 to xn, y1 to yn, and let's say x1 to xn maps P to 0, right? So then P comma 0 goes to the origin, 0 comma 0 in R2n. Now, what is a neighborhood in R2n? Any neighborhood of the origin in R2n, it contains a ball cross a ball, right? Some ball of radius epsilon cross a ball of radius epsilon, right?
Yes. Yes.
Any neighborhood of the origin in R2n, it contains a ball cross a ball.
Yeah,
Now,
but-
ball cross a ball means what? It means norm x less than epsilon and norm y less than epsilon, right? So now you go back to the manifold Tm, norm x less than epsilon will mean a neighborhood V of P, and norm y less than epsilon will mean, well, if I choose another epsilon prime small enough, that will contain tangent vectors V with norm V less than epsilon prime, right? So we'll get a neighborhood of this form. Is this clear? Yes? Yes?
Yes, sir.
Yes, sir.
This is okay. So then we're done, right? Now define gamma from minus delta comma delta cross script U to M by T comma QV maps to pi of alpha QV of T, where pi from Tm to M is the natural projection. Is this clear? So this is explicitly the map gamma. Is it okay?
Yes.
Yes? All right. So that proves this proposition. And now we need another lemma. So what I want to do is basically, I want to say that if I make epsilon small enough, then this neighborhood, this time of definition minus delta delta, I can make it a uniform interval independent of P. I can make it defined for time 1, at least for time 1. Okay. So the way to do that is by the following lemma, which is called homogeneity of geodesics. So if T maps to gamma of TQV, this is a geodesic defined on the interval minus delta comma delta. Then if I look at the geodesic T maps to gamma of TQAV, So I have the same initial starting point, but I multiply the velocity, the initial velocity, by a positive scalar a. Then I get another geodesic. This geodesic will be defined at least on the interval minus delta over a up to delta over a. All right. And moreover, this geodesic is given by just a rescaling in the time variable. So gamma of t comma q comma av will be equal to gamma of at comma q comma v. Okay, so multiplying the initial velocity by multiplying the initial velocity by a corresponds to rescaling the time by a. Okay, this will also be a geodesic. So how do you prove that? That's from the following exercise, which I'll do for you. So if I take any curve gamma and I look at a new curve, which is just given by rescaling the time, so h of s is equal to gamma of as, then the exercise asks you to show that dds of h dot s. So note that h dot will be a vector field along the curve h. The curve h is not the same as the curve gamma. It's a reparametrization of gamma. Okay. So dds of h dot s, this will be equal to a squared times ddt of gamma dot at the point as. Okay, so I mean, if we were working in Rn, this would be obvious, right? Because this dds of h dot will be just h double prime. And so h double prime would be s, you differentiate twice, each time an a comes out. And so h double prime would be equal to a squared gamma double prime of as, right? And so this formula,
is it going to be dds on dd?
yeah, this is dds of h dot at
On the
s.
right-hand side.
Yeah, this is ddt of gamma dot.
So t equal to as.
Sorry?
T equal to as.
No, t not equal to s. It's a dummy variable, right? It's a dummy variable. So you're saying t is equal to as, but yeah, I mean, that's the change of variable, but this just means the covariant derivative of gamma dot.
Yeah.
So this is a vector field.
Yeah, small t.
This is a vector field along gamma, right? So along gamma, the variable is t. So this is ddt of gamma dot. This evaluated at the point as. Okay. Is it all right? So we'll prove this. There's just a minute remaining, so we might as well stop now, and I'll prove it in the next session. Okay. So maybe you can stop the meeting now and let's just start again in the next session.